Okay, let's continue our discussion. Today we are going to discuss example 6.8, and what is happening here. A metal bar, let's say this is metal bar, and this metal bar is 70 centimeter long and 4.004 kg mass, and supported, let me write it here, mass of this metal bar is 4 kg. Okay, now two knife edges placed 10 centimeter from each end. So let us say one knife edge placed here, K1, and another here, K2. And as it is given, this distance is 10 centimeter, and this distance is also 10 centimeters. Now, next, a 6 kg load is suspended at 30 centimeter from one end. So let's say from this end here, a 6 kg mass is suspended. So I can write it in terms of force also, and then this distance will be 10 up to here, and from here to here it will be 20 further. Only then it will be total 30 centimeter. So let me write it here so that we will have ample space. So this is further 20 centimeter. Now find the reactions at the knife edges. Okay. So what is happening here? This metal bar has mass 4 kg. So if we are taking, this is uniform. So if we are taking its center of gravity, it will be at the middle. Means if the entire length is 70 centimeter, it will be at 35 centimeter from its end. Okay. So this will be 4 kg, and corresponding to this 4 kg, there will be weight, and this weight will be 4 times g, where g is acceleration due to gravity. And now we have to find out the reactions. So where are these reactions? So one reaction, normal reaction, will be here due to this knife edge K1, and this normal reaction, let's say it is R1 upwards, and another will be here. This will be R2 upwards. Okay. So up to here, all good. Now we have to find out this R1 and R2. And if this bar is in complete equilibrium, then the net torque and the net force on this bar must be zero. So let me write here a point and here another point. Okay. Now in the first case, if we are taking translational equilibrium, so total forces acting on this metal bar should be zero, means resultant of those forces should be zero. So what are the total forces acting? Here there is another force acting, and this is due to this 6 kg body. So let's say this is W prime weight, and this weight will be 6 times G Newton. Okay. Now we can write what are the total forces acting on this block, on this bar. So R1 and plus R2, this is upward direction. This is also acting along upward direction. So these are along the same direction. We can add them, and then the total force upward should be equal to the total force acting downward. So that is W prime plus W here. So we can write 6g plus 4g, that is 10 times g Newton. This much force. Or if we are taking g equals to 9.8 meter per square second, so this will be 98 Newton. Now coming to the second part, in case of rotational equilibrium, this is for translational equilibrium. Okay, so in case of rotational equilibrium, the net torque should be 0. So we have to choose a reference point about which we are going to obtain all the torques. So if we are free to choose, as we are free, because in case of rigid body, torque is independent of choice of origin. So we can choose at any location which is convenient to us. So let us choose at this point origin. So let's say this is origin, and about this point we are going to check all the torques. So what are the forces due to which the torque will be here? So one force is here, and this is R1, and this force is not going to give any torque because this is passing through this origin itself. Now the second force will be this W prime. So what will be its position from this origin? This is 20 centimeters. So we can write due to this W prime, let's say there is torque T W prime. And if you know that R cross F is given as torque, and you can find out what is the direction of torque due to this W prime. And if you are using the right hand rule, you can easily say that the torque due to this W prime will be inward. So we can write torque due to W prime inward. And as this W is also acting along the same direction, so due to this also the torque will be inward here. Means perpendicular to this plane of this screen and acting towards inward. Okay, now what about this R2? Due to this force, torque will be acting outward here, means perpendicular to the plane but coming outward. So these two torques are inward. So sum of these two torques should be equal to magnitude wise, because we know the directions now. So sum of these two torques should be equal to this torque. So TW prime plus, I'm saying it T, although it is tau. We have discussed this thing also. So this should be equal to this R2. Okay, what is TW prime? So let me write it here. TW prime will be R cross F. And if we are doing R cross F here, so sine theta will be 1 because theta is 90 degree here. And in all the cases, theta is 90 degree. So we can directly write R into F here. What is R here? So 20 centimeters times 6G. So here we can write 20 times 6G. And here it will be unit of torque, that will be Newton, and this is in centimeter, so we can write it in meter also, but let us say this is in centimeter and there will be something here. So I'm not writing unit right now, because to get it into SI system we have to change this 20 centimeter into meter, which will be 0.2 meter. So let us write only magnitude here without its unit, although it's not a good thing to do, but for time being it will be okay, because ultimately we are here getting torque on both sides, so these units are going to be nullified at the end. So next TW tau due to this W will be, look, up to here is 20 and further this is 5. This is 5 centimeter further. So this will be 25 into 4 times G. And what about this torque due to R2? This will be how much? So from here to here, what is the distance? We can write it easily, because total length is 70 centimeter. Total length is 70 centimeter here, and 20 centimeter we have to subtract, because from here it is 10 centimeter and this end is also here, and from here this R2 acting before 10 centimeters from this end. So ultimately this length will be from here to here. This length will be 50 centimeter only. So we can write here 50 times R2, whatever the magnitude of this R2. Now we can continue. So we have now 20 times 6G, or we can write it 120 G. Okay, let me write it directly. 120 times G plus this is 100 times G equals to 50 times R2. And then this will be 220 times G divided by 50 equals to R2. And then R2 equals to 22 into, let us take its value, 9.8 divided by 5. So why we are not bothering with units here? Because look, centimeter is also here in this, centimeter is here and centimeter is here. So at the end, this unit is not going to appear. Otherwise, we would have taken in meters, 0.2 meter, 0.25 meter, 0.5 meter, and such. So R2 will be, this will be in Newton because this is a normal reaction, means a kind of force. So we can calculate this thing, and this should be, let me calculate it first, then I'll write it here. 43.12 Newton. Okay, now from this we can calculate what is R1. R1 is nothing but 98 Newton minus 43.12 Newton. So we can calculate R1 now. So R1 plus R2 is given as 98 Newton. Then R1 will be 98 minus 43.12 Newton. And then we can write point zero zero. Then it will be 8. And then 43 here will be 97. Then it will be 4 and 5. So this will be 54.88 Newton. So we have found out both the normal reactions here. Now moving to the next example. So here we have the next example. A 3-meter long ladder weighing 20 kg leans on a frictionless wall. Its feet rest on the floor 1 meter from the wall as shown in figure 6.27. Find the reaction forces of the wall and the floor. Okay. So let me describe here what is happening. So this is ladder. This is ladder here. So, okay, this is not going straight, but this black straight line is ladder here now. And this is wall. This is wall here. This is wall. And this is foot. You can say feet because there are 2 feet. So this is feet of the ladder. And here at this point, this ladder is resting against the wall. Now, we have to find out reaction forces of the wall, that is the force acting on the ladder here and the force this F2 acting on the ladder here. So in this case, the only force acting on the ladder is the normal reaction force due to this wall because this wall is frictionless. And in second case, it has normal reaction due to this floor as well as a friction also there, which prevents this wall from sliding this way. So in second case here at the floor, this ladder is experiencing one normal reaction here and another friction here. So we have to check the net effect of these two forces as the reaction on this ladder due to this floor. Okay, so now we can start our discussion how we can solve it. So once again, we are going to apply the same concept. If that is, it is in mechanical equilibrium, then we can say the total force should be zero, means net force should be zero on this ladder as well as net torque should be zero. So I am writing directly here for the first case for translational equilibrium. What are the forces acting on this ladder? So one force is here F1 and another force is here W, and then one force is here N, and F2 is a resultant of N and F. So for time being, I'm going to keep this away from our business. So F1 is there, N is there, this F friction force is there, this weight, and we are taking this ladder to be uniformly distributed. So the weight is acting in the middle of this ladder. So this is weight force. Now, for translational equilibrium, all the horizontal and vertical forces should be balanced. So this F1 should be equal to F. In terms of magnitude, it should be equal, and in terms of direction, it is just opposite. Second, the vertical force N, which is normal reaction due to this flow on the ladder, should be equal to the weight of this ladder. This is weight or gravitational pull on the ladder, which we are considering that this pull is acting on center of gravity of this wall. Okay, so these are the two things we are getting from translational equilibrium. Now, what about rotational equilibrium? So, in case of rotational equilibrium, let's take a second. We have we have to choose any reference here. So, if we are free to choose reference, we should choose it wisely so that our work will be less complex. Okay, so I am choosing the reference at point A. Here we have force N and force F. So these two forces are going to give us net torque 0 because these two forces are passing through origin. So each individual force is giving us net moment of force 0. So now we have to be worried about this force, weight force here means gravitational pull on the ladder, and this normal force. So just a moment. Okay, now we can continue. So, if we are taking here origin or reference point, we should know what is the perpendicular distance. Let's say this is line of action for F1. So, this will be perpendicular distance, and this perpendicular distance we have already here. So, it will be 2 root 2 times F1, and this should be equal to, because look, this is position vector and this is direction of force. So, R cross F, tau due to means torque due to this F1 or moment of force at this point will be directing outward. Now, what about this? This you can see easily if we are going to further extend this vector. This is downward and this is position vector for this weight force. So here we have R cross F and it is pointing inward. So torque due to this weight is pointing inward. So net torque outward and net torque inward, this should be balanced. So here one we have found out. Now we have to find out this perpendicular distance here. This perpendicular distance we need to find out. And how can we do that? So for this we have to apply geometry here. And let's say this is triangle A, B and C. So in triangle A, B, C, if you can remember Thales theorem, which you have studied in your secondary, higher secondary, maybe maths. So if you can remember that, this point E is at the middle of A and C. Because look, Thales theorem, what it says, if this line DE, here, let me make it little bit clean. So if DE here, if DE is parallel to this BC, then this AD by DB will be equal to AE by EC. This is Thales theorem. So you can say that if this is acting at middle of this side of this triangle ABC, then this AE and EC are also equal because this E is also at middle. Using this thing also you can say. So if this is from here to here 1 meter, this AE should be 1 by 2 meter. So we can write it here 1 by 2 times this force. Now we can go further and obtain what are the values for these all things. So N equals to W. So we can write it W equals to, what is N here? So this is normal force and we have W here. What is W? W is nothing but weight of this ladder. And if this ladder has mass of 20 kg, the weight of this ladder will be 20 times acceleration due to gravity. So this weight will be 20 times 9.8 meter per square second. So ultimately it is coming in Newton. So we can write 196 Newton. So if we are getting weight 196 Newton, half of this weight will be equal to this much. So F1 will be Look, this N is normal force. This N here we are using Newton, which is SI unit of force. So not to be confused. Let me write it N prime here. This is N prime. So this N prime is normal reaction due to flow on the ladder. So F1 will be how much? 196 divided by 2, and again this is going to be transposed this side, so it will be 4 root 2 Newton, and we can calculate how much it should be, and this will be 34.6 Newton. You can calculate by yourself. So here we have got the reaction force due to the wall on the ladder. So first part we have done. Now what about the reaction force due to floor? So let me uncover this part now. So this F2 will be sum of these two forces. So we can vectorly add them. And now we have N. What is N now? N is, we have written it as N prime here to be distinguished from this N, which is we are using as SI unit of force. So this N prime will be equal to this weight, and we have this thing already here. Now F1 we know, F1 is equal to F. Yes, here F is equal to this F1. So we have both things here, F and N prime. So let me make it a little bit clear. Okay, so we can write F2 from this. F2 will be under root N prime square plus F square plus 2 N prime F times cos theta. Theta is 90 degree. That's why this term I am not writing, because cos 90 will be 0. So no need to write further these terms. Now what will be here? N prime square. What is N prime? N prime is this force, which is equal to this weight. So it will be 196 square plus F. F is equal to this one. So this will be 34.6 square, and then a square root of these two terms. So this will be, let me calculate it and write it. So this will be nearly 199 Newton. Now what about, because forces are vector quantities, so we have to find out directions as well. So in this case, F1 is perpendicular to this wall, and F2 we can find out its direction with horizontal. So let's say the angle between F2 and horizontal is something alpha. So this is F2 vector, and this is N prime. I am just shifting it here. This is N prime, as this is N prime. Okay, excuse my drawing here. This is F2 vector, and then this will be N prime, and this is F, that friction, and this angle is alpha. So we can write easily that tan alpha will be magnitude of this N prime vector, that is N prime, divided by magnitude of this F vector. So what is N prime and what is F? We can write it. This is easy now. So here we have N prime is equal to weight. So it will be 196. So 196 Newton, and Newton will be nullified here. So it will be F is nothing but equal to F1, which is 34.6. Then alpha will be tan inverse this value, and now you can find out this value as well using chart or calculator, whatever you prefer to, but you can find out this also. This will be nearly 80 degree. So we have found out the reaction forces on the ladder due to the floor as well as due to the wall. So that's all for this video.